Einstein was an interesting man. I can't imagine thinking the way he thought. It's probably why I'm not a genius. But Einstein's theory of relativity. So he also had a special relativity theory that was actually tested in almost the 1900s, not quite. But basically Einstein said nothing can go faster than the speed of light. Okay, well, I mean, if you're driving in a car and you throw something out the same direction as you're going in the car, you should, by physics, that whatever you're throwing, in this case it's a bullet, but whatever you're throwing should have the speed of whatever you tossed it with plus the momentum from the car. And so therefore, if you're throwing it in the same direction, it should be going faster. Right? And so light should be the same thing, right? If you're in a car and you point a laser pointer out the window, the light of the laser pointer should have that speed plus the speed of the car, right? That kind of makes sense via physics. However, they did test after test after test after test, and the light got there when the light got there every time. Did not matter if the car was going in the wrong direction, the same direction, faster, slower. The speed of light was constant. Okay, so Albert Einstein came up with this special theory of relativity, 1905, to help explain why is the speed of light basically the speed limit of the universe. So let's break it down. Part 1, speed of light is the maximum possible speed. It is the speed limit of the universe. Speed of light is the same for all observers. Doesn't matter if you're moving towards or away from the speed of light, you can see it at the same time. And the principle of relativity says that all laws of physics are the same for all observers. Right, so that's kind of the easy part. Speed of light is the speed limit of the universe. Got it. Okay. This is where it gets fun. The universe has no absolute frame of reference. So there isn't a point where we can be like, okay, this is a point in the universe where we can measure the speed of all objects. And we can compare them to each other, and we've got a baseline. There is no baseline. There's only relative velocities between two observers. So he's basically saying the theory of relativity, everything is relative. The universe has no absolute. So part 3 is space-time. Not space-time, space-time. Space and time are not independent of each other. Space does not have an absolute time. Time depends on the speed at which something is moving. And actually, there was a really cool Doctor Who episode about this. I know I'm going to geek out on you right now. But they were in a spaceship that was close to a black hole. And as you got closer to the black hole, your time went slower than if you were away. Or was it your time went faster? But anyways, the spaceship at one end, time was moving fast. At the other end, time was moving slow. And so the time depended on the speed at which you were moving. The people at the front were moving faster. People at the back were moving slower, and as they were trying to get away from this black hole. And so it was kind of neat. What was 2 seconds for somebody at one end of the spaceship was a month for somebody at the other end. And to see the dynamics of that was really neat, played out in a TV show. Alright, sorry. Tangent. Alright, so this is where Einstein starts to get weird. You thought that was it. No. No. So, here is his general relativity. He must have had way too much time on his hands. I don't know. Thought experiment. So he sat down, and instead of doing an experiment, he just thought about one. Okay, so this is what he thinks about. I don't know. Uh, you're in space. Okay, so picture yourself. You're in space. You're in an elevator, and there are no windows. Okay, so you don't know what's going on. You're just floating around in a box with no windows. You're completely weightless because you're in space. And then you start to feel weight. Why do you start to feel weight? Did you come close to something that had a gravitational pull and so it starts to pull you down? Or did the elevator start to move up and so you start to feel weight? And as he thought about this, he realized you can't tell which one it is because you're in a box without windows. You don't know where you are. You can't really tell if the weight's coming from up or down. There's just weight. Yeah, that's where he kind of loses me. I'm just going to trust him on that one. So he came up with the equivalence principle based on that. Is the weight due to gravity, or was the weight due to your frame of reference? Because remember, there's no absolute frame of reference according to Einstein. So, okay. So because of this, Einstein worked gravity into his special relativity. And after working on the effects of gravity, he concluded that space-time is curved. What now? Space-time curves? Yeah. So you're thinking, well, time is pretty linear, right? This happens, and then this happens, and this happens, and this happens. Right? Yeah. No. So particles, us being particles too, can move on a curved path because they follow the curvature of space-time. Okay, so if you follow the curvature of space-time along the same line, it kind of looks like it's linear, but it's not. Larger objects are going to curve and warp space-time. And the larger your object, i.e. how much more mass you have, can tell you how much more curvature there's going to be of the space-time warp. So his general relativity theory says that all matter, anything with mass, can curve or warp the space around it. So anything with mass. He didn't have a limit. He just said anything with mass can warp space. Wow. Alright, so if you're like me, you're going, I have mass. You think I can curve or warp space-time around me? If I could be invisible! That's probably not what Einstein meant, but if it crossed my mind, it had to have crossed his mind, right? Just saying. Okay, here's actually a kind of a good example of what that actually means. Not that you're going to be invisible, unfortunately. So if you take a pool table, right, and take the top off and put a trampoline on it, okay? Then you drop a rock in the center. The heavier the rock, the more your trampoline is going to sag, right? Now try playing pool. Well, I am so bad at pool, that might actually help me. But the ball is going to go around, hopefully, that hole or into that hole, right? But it's not going to go straight. If you hit it straight from end to end, it's going to deflect somehow. There's a large family of people, and this is straight from your textbook, but it's actually a good analogy. Large family of people standing on a trampoline, okay? And they decide to have a family reunion in one part of the trampoline. Okay, it kind of does sound like something my family would do. I'm not sure why, but yeah, it does. And so one person, i.e. me, I'd be like, yeah, you all go, I'll catch up, right? So they all start going one at a time until start, you can see the trampoline start to sag, right? And I'm off in the corner going, let's just see how this turns out. So I start sending messages to them, right? Rolling a ball back and forth. Hey, just finishing up some work or something. How's it going over at the family reunion? They roll back a ball. It's awesome. You should so come. And I'm like, yeah, that's okay. So now these balls are kind of like light. Okay, so just imagine light going back and forth. It's kind of like texting now, right? It just sends out in data. So more and more of your family gets down into this trampoline and it starts to sag more and more. So it's harder for these balls to get out back to you, right? So the light to get out back to you. So they're becoming less frequent. And then finally, everyone goes except you, and the trampoline kind of pinches off, right? It's sagging so much, and that's what D's showing. It's pinching off. And so nothing is able to get out to tell you how much fun this reunion is. I'm looking at that picture going, you're all crammed in there. That ain't going to be any fun anyway. But, they're having fun. They just can't tell you because nothing can get out. It's pinched off. So the rest of your family is cut off from you. And there's no more communication. Balls can't get in, balls can't get out. No more communication. This is kind of the way black holes work. There's so much mass at this one spot. It's curving space-time that it's pinched off. So black hole, gravitational field where the space-time curvature is so extreme that not even light can escape. So space-time has folded over on itself and nothing can escape the event horizon. Whatever is in there is trapped and it disappears from us. We can no longer access it.